Thank you. Good morning. It's a pleasure to be in Dallas. I have been able to visit 2 new US cities in the past couple of weeks. I was in St. Louis last week and Dallas this week. Unfortunately, I went back to a meeting in Chamonix, so I spent much of the past, I think I spent about 2.5 days on a plane in the past couple of weeks, and I've picked up some sort of throat infection. So I'll try not to cough into the mic too much, but please forgive me if I do. So I'm sort of pleased to be here to talk to you today about the LHC Computing Challenge. It's something that I've probably been working towards for about the past 10 years. It certainly seems that way, but fortunately the LHC is about to start next year, and we'll finally see the data coming from the experiment. So we'll find out whether we were ready or not, whether we've met the challenge this time next year. So the outline of the talk is, I guess, fairly standard. I'll give some sort of introduction to CERN and the experiments, as that's what we're all dealing with. Talk about the computing for LHC, which is really the general high-energy physics computing style, and then from that, mention the challenges, bring out the challenges and go through those as I see them that we've been addressing over the past few years. And then maybe a one-slide summary or conclusion. So, so starting then with the introduction to CERN and the experiments. These are the nice slides that everybody was asking this morning about, that are produced by our publicity people. So CERN, they say, is the fastest racetrack on the planet. This probably is an accolade that belongs to Fermilab at the moment, I would guess, because the LHC isn't yet in operation, as I've mentioned. But we have this accelerator about 50, 100 meters underground here crossing the Swiss-French border, going around there, with these sort of magnets to bend the bunches of protons around as we accelerate them, and then keep them going around to produce collisions in the detectors. So they race around this 27-kilometer ring at some vast fraction of the speed of light. So this is this wonderfully fast racetrack. And whilst they're going around that, it's absolutely crucial that they don't hit any other particle to lose energy, to collide, to scatter energy into the magnets, or anything goes wrong. I mean, these magnets are worth $500,000 a piece, and the beam energy in a bunch of protons can melt several kilograms of copper, so you certainly don't want anything going wrong. You want nice empty vacuum there, and as they say, 10 times less anything there than there is on the surface of the moon. That again, I guess, is when we start operation. It's not a vacuum at the moment. It certainly is today, though, or certainly about a quarter of the accelerator, one of the coldest places in the universe. To be able to create the intense magnetic fields that we need to bend these high-energy particles around the accelerator, they have to be superconducting. So already you have to be fairly low temperature. And then you have these magnets that are about 50 feet long. So to get all of them very cold and evenly cold, we use the properties of superfluid liquid helium, so it can infiltrate absolutely anywhere in these magnets, go through and make sure there's a nice even temperature. You don't get any sort of temperature gradient once you've got superfluid liquid helium involved. So this is at 1.9 degrees Kelvin, so this is less than the 3 Kelvin outer space, so one of the coldest places in the universe. And in contrast, one of the hottest spaces then, when we have the collisions, intense energies in very tiny spaces create intense heat, recreate the conditions of the Big Bang to allow us to understand some of the properties something that's happening at the beginning of the universe. And then, despite these tiny collisions that we have these huge, sophisticated detectors. I don't know if anybody can really see, but there's a person standing about there, or about here if you're looking at that. So there's a person standing in this set of magnets for the Atlas experiment. Atlas, I think, is it's about 20 meters so it's pretty big. And they're also massive in terms of the number of electronics channels that they have, and that is clearly the important point for the computing. We have a lot of silicon strip detectors with massive number of channels deep in the heart of the detector, which has been built in since then, that create a lot of the data. So why do we do all this? Well, because it's fun, certainly, but really to push back the frontiers of knowledge. So what is mass? That's one of the key questions. We have, particle physics has this equivalent of the periodic table. This is the standard model particles. In the top, the quarks and leptons are the particles of matter, and they're held together by the force particles at the bottom there, the photons, the gluons. This is a very successful description of the world, of the universe. But we don't know why the particles towards the bottom of matter here are heavier than the particles in terms of the top. Now, there's a theory that there is a field in space that interacts with these particles and gives them mass and slows them down. And it's a field called the Higgs field, which is named for this person here, Peter Higgs, who thought this idea up. And the idea is that particles interact with this field, and the more you interact with it, the heavier you are. And the analogy that's given, that I know of, is often given in terms of UK politicians. Now, I won't tread onto dangerous territory by mentioning any American politicians, but I'll try and do it in terms of computing people. None of you know me, or certainly didn't this morning, so I walked from the back of the room to the front in the showcase or the pizza parlor or wherever, and I can walk easily because there are no interactions. None of you know me, so I can walk quite quickly where I want to go and move quickly. I have low mass. Then you imagine somebody, I don't know, Richard Stallman, Bill Joy, somebody like that, who you all know of, and he walks in, and everybody wants to talk to him and say, hey, how are you doing? What's the latest thing going on? And there's a lot of interactions with a field of people, and he can only walk slowly to the back of the room, and that's the equivalent of a heavy mass particle. So these interactions with the Higgs field are what give particles mass, and there should be a particle of that field, a Higgs particle, which we hope to discover at the LHC. Now, if we don't, there'll be a lot of physicists who will be very happy because it means there's something wrong with the theory and we'll have to dream up a new one. There'll be a lot of financial people who might not be so happy, though, because they've paid a lot of money for this, but it will be an important physics discovery. Similarly, we want to understand some of the missing matter in the universe. Our partners, the astrophysicists or the astronomers, look and see that as galaxies rotate, they don't rotate in the way that they would do if they only have matter that they can see. Now, part of the physics theories to go beyond the standard model suggests that there are partners to these matter particles called leptons and squarks, sparticles, supersymmetric partners, and similarly supersymmetric partners to these force particles. So gluinos and photinos and winos who come in. So these supersymmetric particles could be some of the missing matter in the universe, some of the dark matter in the universe, something which covers the rest of the mass that we don't know. And these also could be discovered at LHC. Then why is there no more antimatter? I'll come back to that briefly later. And similarly, recreating really the intense energy densities that were in the Big Bang. So these are some of the reasons why we do it. Along the way, we also developed new technologies. Now, this isn't what we set out to do. We didn't set out to develop the web. It was a tool that was needed to allow the physicists to communicate. We don't set out to develop medical imaging devices, but the particle detectors, the imaging detectors that we create are very useful in those fields later. So these are useful spin-offs from CERN. And similarly, now some of the scanning issues at airports, I've been through a lot of those recently. Some of the imaging detectors, again, spin-offs for that. So these are useful spin-offs from the work which is done at CERN and in general at other high-energy physics laboratories. Then CERN is a great place for uniting people from different countries and cultures. It's a wonderful place to work to today, meet people from everywhere. But more seriously, it was a goal, an explicit goal of CERN in the 1950s. One of the goals was to unite the particle physicists in Europe who had so recently been on different sides during the Second World War. So it was definitely a unifying idea. It's a very open place. There are no secrets at CERN. We welcome everybody. So it's a really great place for that. And then to train people for tomorrow, not just in physics, but in a range of other fields. Building the LHC detector has been a huge civil engineering exploit. So there's a lot of technology transfer that goes on in those. But this is all the publicity stuff. Here's a more interesting picture of the detectors. This one is called the compact muon solenoid. Now, it's clearly not compact compared to a 5 or 6 story building. It's only compact compared to its big brother, Atlas, that we see here. So zooming in on Switzerland, there's Geneva at the end of the lake. Here's the ring. Here we have CERN there, like a university campus. The Atlas experimental pit head. Down underground, we have a cavern there, which is big enough to hold Notre Dame Cathedral in Paris. Massive cavern. And here we have the detector. Which, as you can see, is big enough for the standard physicist to walk through. So really, massive devices, with many channels, all to detect events from the collider that we have here, and which is building on the accelerators that we've had at CERN since the 1950s. So the particles start off in these smaller accelerators before going round the LHC into the LHC, where they pick up energy, still more energy, till they're at, I think it takes a couple of hours to pick up the coast energy before they have the right energy for the collisions in the heart of the detector, which produce pictures like these that you see here, with all the massive number of channels that we have involved. Okay, so that was the introduction to CERN and the experiments. I'd like to sort of turn now to the point about the computing. So really the point about these is that the 4 of the LHC experiments. Now we've seen Atlas and CMS, but there are also 2 others. One of them is Alice. Now this is the point about the Big Bang issue before. The purpose of Alice is to collide or to study the collisions of lead nuclei. Now there you get really intense energy densities in the collisions, many particles coming out, and a huge flux of data from Alice when we're in heavy ion mode that we'll come to later. There's Atlas and CMS, the 2 general purpose experiments that I mentioned, and they're not to the same scale. The person there is one of these dots here, so they're not to the same scale. And then LHCb is this experiment to look at why there is this asymmetry between matter and antimatter. So that's a rather special experiment, which is why it doesn't look quite so like any of the others. But the point is, all of these generate huge amounts of data. So there are something like 40 million particle collisions every second in the heart of the experiments, which are turned or reduced rather by the online computing systems of the experiments into a few hundred good events each second. Now there are immense challenges in doing this reduction by the online computing that I'm just not even going to touch on, but going from the 40 million events per second, data rates that are talked about like all the world's phone conversations at once, down to the rates that we have here, is also a challenge that CERN and the LHC experiments have had to address. So these events that are liked are recorded at around 100 megabytes a second. It's around 200 to 300 for Atlas and CMS in proton-proton mode, and over a gigabyte a second for Alice in heavy ion mode, 1.2 gigabytes a second. So if we take the raw data and all of the process data that these experiments produce, it's going to be around 15 petabytes a year. Not 2008, but 2009, 10 maybe, in steady state mode. And for those of you that can do pattern recognition very quickly, there is an event hidden in there. If you look at slightly more high energy tracks, this is an event showing a Higgs decaying into 4 muons. So this is a sort of signal teasing out that signal that the whole computing for the LHC experiments has to do. So what are the different steps then in this data handling and computation? Well, the thing that I should probably mention, although it's not on this slide, as maybe it's so obvious to me, is that the key factor of high-energy physics computing is that everything is trivially and massively parallel. We have these hundreds of millions of events that are all individual events that can be processed individually. There's no connection between them. It's only a statistical connection later that shows us that we've found the particles. So it's easily and adapted to computing on massively parallel computing farms with no communication between them. So this is farms of Linux PCs today with simple Ethernet. We don't need any interconnections. We don't need anything complicated. There's no message passing. But what we do need is a lot of CPU capacity to turn the raw data, which is in terms of signals in an ADC converter or whatever, into a description of a part of the event in terms of a track which went this way through the detector and deposited X amount of energy in this calorimeter over here. And to that reconstruction phase, as it's called, is something where the compute power is actually relatively easily known. You know how much time it takes you to reconstruct a single event, and you know how fast the events are being produced. And you have to keep up with that rate for the reconstruction, because otherwise, once you run behind, then you're never going to be able to catch up again because the accelerator keeps producing the events. So this reconstruction phase sends the data to tape, produces event summary data on disk, and it's a known amount of computing. And it's a well-controlled process because it's only handled by 1 or 2 people on the experiment to produce the authorized version of the data to do the analysis on. The analysis, on the other side, is completely uncontrolled. This is where you have hundreds of physicists at a time that are trying to produce their version of the paper that will win them the Nobel Prize. Well, not quite, but they're certainly trying to do the best analysis they can, refine their algorithms, run over the data again and again to really understand what's happening, and then finally come out with a result. So this is a repeated process which is going on. There are thousands of people in the experiment will be doing this, and hundreds of them will be doing it at any one time. So the more computing that you can throw at that, the better result, the more finely they can analyze the data, the better the final physics result. The last sort of computing then that's involved is simulation. You put in known processes, simulate the way in which they produce signals in the detectors so you can check that you understand what's going on. And here, it can take over an hour on today's boxes to simulate some of the LHC experiment events. So that's a very compute-intensive process. So putting this all together, we need something like a total of 140 million spec-int 2K computing capacity in 2008. That was a prediction a couple of years ago. Now already it's broken down in this chart into capacity at CERN at sites that are called Tier 1s and Tier 2s that I'll come back to. And you can see that CERN is only a small fraction of the overall computing capacity. Already the fact that it's broken down shows you how we've addressed one of the challenges, which is providing this immense amount of computing capacity. And I'll come back to that later in the talk. But if you look at the numbers just at CERN, this is something like 2,500 PCs for the CPU capacity, and you have to throw in another 1,500 boxes for the disk and tape layer, and then you've got things like master nodes for our batch system, various other things. So you've got 5,000 or 6,000 boxes easily to handle for this sort of system. And so when we started looking at this in 2000, just being able to handle this number of boxes was one of our major concerns, especially as then the detector was supposed to start in 2005. So you can imagine we'd have needed vastly more boxes then to provide this level of capacity. Okay, so that was the introduction then to the experiments and to the computing background. What do we see then as the challenges? Well, I think I've covered the first two. Simply providing the capacity is a challenge. Managing the boxes, that's the sort of parochial CERN conclusion challenge, is a challenge. Data management and distribution is another challenge. And then one that I think is coming up recently, what's going on, that I'll talk to. So starting with the first one, the capacity provision. Well, we started looking at this in the late 90s, and nobody was going to put all of the computing at CERN. It was certainly feasible, but it wouldn't have been done for various reasons. And lots of people have their computing. They're not going to give the money to CERN to do that. So it was clear that we would have a collaboration between CERN as a tier 0 center, which is producing the data, storing it long term, and a set of tier 1 centers to whom the data will be distributed. Now, we've collaborated with many of these tier 1 centers in the past. The Rutherford Laboratory in the UK has long been a center associated with CERN computing. Fermilab and Brookhaven perhaps less so, but certainly they've been laboratories that we've been working with in the past. The difference this time is that we're not shipping data, whether on tape or network, a few months after they're produced. The data is sent out immediately from CERN to these centers. So they're online to the data acquisition process, and they participate in the full creation of the final results. So the reconstruction process that I mentioned earlier, going from the raw data to the description in terms of a physics event, that will be done after the data taking is complete. You take data for 6 months, then after those 6 months are up, you've refined your codes, you want to go back and reprocess all of the data again to come up with a better description. And that will be done at these tier 1 sites. So they're really an integral part of the overall system, as was planned. And then we have the tier 2 sites, which really are individual universities. There are around 100 of these in 40 countries. They take the analysis, end-user analysis load, but also the simulation. So they don't have to worry about tape storage, but they're looking at simulation. So we had this idea of a computing service hierarchy in the late 90s, but no real idea of how we would actually bind them together. But then along comes, in a very timely fashion, the grid technology. The Foster-Kesselman's book in the 1999-2000 came at exactly the right time for us. So we created this LHC computing grid project to deploy a service across a grid. This LHC project was not designed to develop grid technology, but rather to exploit it for the physics needs. And so the challenges that we have are to deal with the worldwide nature. So there are lots of competing versions of the middleware that should be used in Europe and America. And the newness of technology, which again meant there was lots of competing middleware from different teams trying to say there was better. And of course, the sheer scale. So the LCG service relies on 3 major grid infrastructures. Certainly the 2 large ones, EG in Europe, the yellow dots that you see here are all EG sites, OSG in the US, and then NordiGrid is a much smaller grid in the Nordic states in Europe. So building a grid on top of these 3 infrastructures was a major challenge. You have to create the interoperability for users. They just want to submit a job from one place to another. Now, a lot of this is eased because although there are different grids, they generally use things which came out of Globus and the VDT toolkit from Wisconsin. But allowing a user from Liverpool, where I was, say, to submit to a university in Dallas, there probably is one participating in LHC, required a lot of work on interoperability. And also a lot of background work on administrative issues. So identity management, certificate authorities. There's an International Grid Trust Federation which has been built up, partly driven by our need to have certificates that are allocated in Europe, recognized and agreed to be valid by people in the US, so that I don't have to get the certificate from somewhere else because I don't have the right policy management system for the unit that gave me a certificate. Monitoring was a challenge as well. We want to see what's happening in the grid as a whole, so we want to monitor from CERN what's happening at a university anywhere, and similarly perhaps universities anywhere want to monitor what's happening at CERN. And certainly we need accounting to say how much CPU has been done. And it does work. I know this is a challenge which has been met. This is a snapshot of the grid in action. It's probably at least a year old now, so these dots would be larger in terms of the number of jobs. But you can see jobs working at many different universities. When you see this working in live mode, there are jobs which whiz along these lines as they're sent from a resource broker to a site which has the facilities to accept the job, both in terms of spare CPU resources and also in the data that wants to be analyzed. So the data is sent, the jobs are sent to where the data are. And it is a thing which is an operation. And other people think so or have believed our press releases, as we've been recognized as one of the, I think it's the 4th of the 7 wonders of the IT world recently by the CIO site, as you can see there. If you look briefly at the counted CPU usage, again, you can see it's being done. There's a breakdown which remarkably fits very well between what is actually being done to the prediction in terms of the breakdown. Some fantastic number of spec-int 2K days per month are being delivered by this system, and it provides access to everybody to some 9 petabytes of disk. So creating that grid service across multiple infrastructures is a challenge that we've met successfully, but there are still others that remain. Reliability is an issue. This is an issue. Plots shows the reliability which is expected to be achieved at CERN and the tier 1s. Now, we have to get up to something like 95% next year, but we've been struggling to reach the target this year of 88, and then it rises at the end to 91. You can see that we've been improving in reliability over time, but it's not steady progress. There are improvements, and then we drop back as maybe new services are introduced. So getting to the reliability that we need will be a challenge. And thinking about it the other way, it's clear that we're not going to get to 100% reliability. So you've got this massive data which is coming out from the LHC experiments, and you have to face up to the fact that that the service out there is not going to be 100% reliable. So you have to cope and react and be able to work effectively with a service which just cannot be 100% solid and reliable given its distributed nature. So that will be that's a challenge both ways. The ramp up. We've got this massive computing capacity. We've known where we've got to get to. So you think, well, you've got to get there over 5 years. You must be able to do it. But of course, in computing, everybody wants to spend the money at the last minute. So we have to increase the CPU capacity by a factor of 4. Now, this is a slide from, I think, June or July this year. So 4 in a year. Now it's a factor of 4 in 6 months that we have. So there's a huge amount of kit which is being rolled in or has to be rolled into these sites. There's a challenge there. Factor of 4 for CPUs, factor of 6 for disk. There's a massive ramp up which is needed between now and next April, May. And then collaboration. This is a sort of non-technical challenge, but it is an issue that maybe some of the people in this room will worry about. I mentioned the creation of a grid trust federation, which has to work with collaboration, and so this clearly can be done, but there are changes. A tier 2 site where once a system administrator at a university site controlled the systems, understood what was going on, now it's part of a bigger whole, and there will be some central decision on what software needs to be installed at a university. And conscientious system administrators like yourselves will be looking at some of this software and saying, well, hey, I don't really understand that, I don't like that. That's not compatible with my policy for testing secure software and installing things with root privileges and so on. So there has to be a move to introduce these software systems in a consensual manner. And there are issues there that we have to deal with that are non-technical. Okay, box management. Moving quickly through this. I think this is definitely a CERN-specific take on where we're going in terms of how we manage the large number of boxes. But there are issues in terms of installation and configuration, monitoring, and also the workflow for the 5,000–6,000 boxes that we think we need. So back in 2000, 2001, together with people in the European Data Grid project, there's some idea that what you had to do was make sure that a node couldn't move anywhere. It wasn't allowed to do anything by itself. It was tightly constrained in a box. And somebody came up with this diagram to emphasize or to illustrate that idea. Now, I actually hate this as an illustration because if you actually look carefully at where the arrows are going, that node is not tightly constrained at all. It's going to shoot off to the right somewhere, my right somewhere. But the principle indeed is showing that it's surrounded by a system which will handle its configuration management, manage the node. You'll have a monitoring system which will see how it's performing, but is also capable of monitoring the configuration and reporting changes back there. And then you have some logistical management system around so that when your node is out with a vendor for hardware repair, you can check that it comes back in 3 hours according to the time that they're supposed to respond in, and not 3 days, as can sometimes happen. So why did we develop something ourselves rather than picking up anything either commercially or open source? And I think the last will definitely be a question, as I see from the agenda of this conference that there are a number of references to CF Engine and LCFG and so on. Well, commercially, one of the points a few years ago, and I guess it's maybe 6 or 7 years ago now, was that full Linux support was rare. More importantly, there's the point that the commercial packages that you could get weren't any labor-saving device for us. We could pay for them provided that we get some reduction in the number of people that we need to support, but these things couldn't do that. They don't provide support for our sort of applications. AFS, I think that comes up later today, we use heavily. LSF, our batch system, and certainly our mass storage system, they didn't know anything about. So we wouldn't save any effort on that. We'd pay money and we still need to put the people in. Open source systems, there were many packages with interesting features. I think I mentioned LCFG, that was definitely looked at by these people, but none of them had all of the items that were considered essential by the people looking at this in the time. The ability to have the hierarchical specification, have inheritance, and to have the overall integration between the configuration management part of the package and a monitoring part and a workflow. So going through these in parts, the installation and configuration tool that we have is called Quator. Key elements of this are the configuration database at the top, holds the configuration templates for all the systems that we have, translates these into XML format for export to the nodes, but also has an SQL backend. You also have information on a node in terms of how much power it consumes, and that's definitely a challenge today in providing the power. And I see there's a session again later today which talks about power for computer centers. So the export to an SQL backend allows you to say how much power am I using in that area of the room. Then it interfaces, not interferes, with an installation manager, so you know what software should be installed on the node, and a software repository. So it's used not just at CERN, but there are a number of places around Europe especially, I think, but a couple in the States that use this. This is an example of the configuration hierarchy, the idea that you only define things where they need to be defined. So we only have one time service at CERN. That can be inherited by all of the different systems. The batch packages are the same across the different nodes. Define them only once. So here's an example, I'm not sure if you can read this, but it's a template for a node which pulls in a hardware configuration and a software configuration. The hardware configuration describes the node in terms of the CPUs, in terms of the disk capacity, so that will determine how you can partition the disk. and various other issues, power, for example, you only specify the power of the node for the hardware type. And then the software configuration, drag in the same software for this node as everything else. And the node itself only needs to have the information which is specific to it, such as its serial number, MAC address, and so on. The software distribution certainly has to be highly scalable to cope with the number of nodes we have. So there's a hierarchy of masters, and using, I think, SQUID proxies with distribution via HTTP. Now, where you've got a scheduled distribution, I'm going to upgrade Emacs tomorrow, you can roll out the RPM today, cache that on the node, and then just snap your fingers tomorrow and trigger the install. So maybe the caching, full caching isn't necessary for that. But where you have a rapid security update to put in place, you certainly do need the caching to make sure that you can get the software to the nodes in a timely manner. This next slide is supposed to show that we can do management quite effectively in practice. You're supposed to be looking at this big leap up here and here for those of you over there, where we were providing boxes through a test for an online test for one of the experiments. And so they took our boxes, reconfigured them, and they also took new boxes that we'd bought, so the batch capacity that we had went down. And then the test finished, and we just changed for all of the nodes, the configuration that it pointed to, and said, install yourself. And then within less than a day, 400 nodes reconfigure themselves and put themselves into the batch system quite effectively and quite rapidly, and with very little human involvement. Okay, monitoring, again, similarly, we need a massive monitoring repository to cope with the data that's coming from all of these systems. Sending it data from monitoring agents sitting on the node, and then providing this all the usual nice RRD plots. So what do we monitor? Well, all of the usual system parameters. So system load, and everybody monitors this, SMART, Oracle, our AFS clients, and this is what everybody would expect to be monitored. We also, though, monitor non-node issues. So things that we get from our building management system. Now, I think this is becoming more common, but the power demand, the UPS status, the temperature, all of these things you need to know about. And with the integration that we have between the monitoring and the configuration and the workflow system, we can, in principle, trigger a power down if we approach our cooling limit, say, or if there's a power cut. We don't do this yet, but certainly with IPMI coming along as an easy interface to the control, we're looking at that. Then we monitor the high-level mass storage and batch system details, queue length, file systems, whatever. And we provide some information on hardware reliability. So again, showing some nice displays, but everybody will have seen the typical plots, an overall sort of portal, as they be called now, to the set of different monitoring information, batch system that we have, CPU usage, load average plots. This, I think, is something to do with Oracle, so I don't understand that, but our Oracle people do. Hardware reliability, so you can see that there was 1 week there, the colors maybe aren't so good for you, but there's a spike sort of here where we had some issue with our hardware failures, so we can follow that. And you can also compare reliability across batches. We buy boxes at 400 at a time. Which one supplier is more reliable? You can monitor that. Node reboots, so you can see when everything was rebooted or when there was an individual node that's rebooted rapidly. And power. This is an example of the power distribution for one of the areas of our machine room. So those are the standard stuff that you can do, but we can start to do interesting things as well because the Lemon monitoring is integrated with the configuration management. So we're continually moving boxes around and dynamically creating clusters or increasing the capacity as we do new things or test new things out. So this shows a plot of the behavior of a cluster when we're testing the behavior of our mass storage system, and you want to track the network utilization. Now, if you can't meet the goals of these tests with the number of boxes you have, and you want to add another one, then you don't want to figure out 2 days later that, our monitoring didn't actually include that box that we just added. So the plot that you have of the performance is wrong because it doesn't take account of that box. So no, because we have this overall integration, you change the attribution of a node in the configuration database from one cluster to another, and automatically that's then taken into account when you produce these plots. There's no need to worry about whether you forget about things. Another interesting example is that you can define clusters on the fly. We're supporting a number of experiments who are all very worried about the facilities and that we provide and how they're performing for them. And we can show them the overall plot of how the batch system behaves. But they say, well, yeah, that's the overall batch system. But we've got a problem with swapping because our memory footprint is bigger and you're not taking that into account and it's being washed out in the overall average. And so we think that our jobs are performing poorly because of that. Well, what you can do is, as a lump said correlation engine off to one side, you can look at where jobs are running on the node, feed that information in, and dynamically build a cluster from nodes which are running jobs for, I think this is Atlas. So this changes over time. For now, it's these 5 nodes over here, and then in an hour's time, it could be 4 of those plus 2 others, and some of those could be running CMS jobs, some of them as well, some of them could be just running Atlas jobs. But the point is you get a measure of the behavior of the system that is relevant to Atlas, and you can compare that to the overall batch system behavior and then tell them that they're being wrong or perhaps find out something interesting. So that's a useful tool as well. Okay, workflow, I think I'll just go through this very quickly. But there's a number of things that you need to do with boxes in terms of hardware. Track where they are when the installation, vendor call for repairs, make sure that they come back on time. When you're moving them around, there's a set of steps that you have to go through. Similarly, with the software state, if you want to upgrade all of a cluster from one version of the operating system to another, you want to make sure that all of the nodes first finish the work that they're doing, secondly, get reconfigured in their configuration profile to the new one that you want, then they're reinstalled, and go through all of those in order. And you don't want somebody to have to follow that for a cluster of 5,000 boxes. You want to tell the state management system, these 5,000 boxes, handle that upgrade, follow those through the process. Okay, so this one was animated, but it just shows the complex web of people and services that are involved when you have to do this. So you have operations staff, technicians who will do the base level reinstall. If you move a node, there's a network database, has to be updated, reallocate an IP address, you have to update the configuration database for the node, and all of these things. And Leaf follows them through that. One last point then on the integration of all of these systems. Some trivial stuff is that you don't want to raise alarms for an operator for a system which isn't in production. If somebody is testing some nice software component on a node, you don't want to bother the operator for that, and that we trivially do. Some of the more interesting ones, though, is this example that I show here, that you've got a disk server that could have a RAID problem. So one of the disks drops out of the RAID array. That happens at 11 o'clock in the evening. It's not a problem, it's a RAID array, the disk has dropped out, the server can carry on. But you know that the next morning, somebody's going to have to come in and deal with that RAID array, and at the very least, it will be rebuilt, and that will be something that is I/O intensive. So the one thing that you don't want to do is have the mass storage system carrying on sending I/O requests to that disk server. You want to route them elsewhere. And this is exactly what we can do. We can spot the alarm, see what's going on. The state management system can be involved, and it can tell the disk server to put yourself on standby. So the disk server says, yeah, I'll go on standby, and tells the mass storage system, well, put me in draining mode, which means that existing I/O transfers can carry on, but don't send any new I/O transfers to me. So the new data coming in from the pit will be routed to other disk servers, which is good. If there are any requests for data which is only on that disk server, then the mass storage system will replicate that data elsewhere or recall it from tape maybe. And all of this means that the next morning when you come in at 8, 9 o'clock, the disk server is sitting there doing nothing and ready for somebody to deal with that problem. You don't have to start handling these problems only when people come in. So this comes back again to some of the issues about being able to deal with things that you know are not 100% reliable. So this level of integration of all of the systems allows us to handle this level of automation. Okay, so what do I think is some level of conclusion here? Well, I think this has been a rather parochial view of what's happening at CERN rather than the other sites, but I would argue that the toolkit that we've developed has allowed us to cope with a significant increase in the box count with a reduced number of staff, and confident that it will scale further. On the other hand, there are major problems still, challenges in the large-scale farm operation that I am worried about looking ahead to the next year. We have something like over 2,000 boxes, 2,200 boxes to install between now and the end of December. That's something that we've never done before. Last year, we installed something like 1,200, and the year before that, it was 800. So we're going up, but 2,200 boxes, physical boxes, 2,600 logical systems is a lot of systems to install and do the configuration for. And also requires, I'm sure you realize, the racks and everything behind and the cooling. So there's a lot of operation problems there. And you have to buy the boxes as well, which given that we're an international organization and everybody wants us to spend money with them, is a long, complex process. And then dealing with the failures again. But I recognize that there are people at the Google scale that are certainly coping with more than that, and maybe some of you are also involved in this sort of scale of issue. Okay, moving on then down the challenge list, data management and distribution. So this is a summary picture which shows why this is maybe a bit of a problem. So we have data coming in from the experiments and an aggregate rate of around 700 megasecond in proton-proton mode, and this is sent out to the batch farm for the reconstruction, and the batch farm sends back around 400 megasecond of reconstructed data. All of that has to go to tape, so around 1.2 gigasecond of data to tape, and then the raw data and multiple copies, because some of the tier ones get more than their fair share of the event description data, have to get sent out to the worldwide grid. So these are data flow rates that we have to deal with. But we want to be able to cope with a factor 2 of above that at least, so that we can catch up if there are any problems. And these numbers I can give because they're scheduled work. We don't actually know what the numbers are once you start throwing in all the end user analysis. You have to cope with higher rates. And certainly you have to cope with higher rates during the heavy ion operation, where the data rate to tape can be as high as 2 gigasecond. Okay, so more on sort of volumes and rates. 15 petabytes a year I've mentioned, peak rate to tape 2 gigasecond. What does this mean in practice? Well, it's 3 full Sun SL8500 robots a year. And that's, if you start looking at in those terms, it looks interesting. Another interesting challenge, is that over time, the experiments will understand their detectors better. There are discrete elements in the detectors, and if a particle goes slap bang into the middle of one of these elements, it's pretty obvious that it will deposit, well, it's not obvious, but maybe it will deposit all its energy there. But what happens if it goes 3/4 of the way over to the edge of the element? Can you sum the energy deposition in that element and the next one and come up with the same amount as if it had gone smack bang into the center of one element? Certainly at the beginning, probably not, but over time, they'll understand this better, improve their software, and when they've done that, they want to improve or reprocess the past data as well. So the first 5 years, it's likely that they want to reread all of the previous data between runs. If you read 60 petabytes in 4 months, that's 6 gigasecond. we can run our drives at 80 megasecond flat out, so you just need 75 drives merely for this level of controlled access in the 5 years, so a fair bit. Another point that is perhaps surprising is that we don't use commodity tape drives. We use commodity CPU servers, commodity disks. Commodity tape drives, though, they have this inability to rewrite today's media at tomorrow's density. You buy tape drives from Sun or IBM, and you can reformat the media or reuse the media next year or in 2 years' time at twice the density. So you copy all of your data over, you use half of the tapes, and then you've got, you know, the capacity that you had originally for free from that. And this issue about media reuse saves a huge amount of money over 5 years. I forget what the figure is in dollars, but media costs we estimate to be something like 2 or 3 million Swiss francs a year by 2012. So this, interestingly, meant that we didn't favor LTO drives for that. Okay. Sorry. Right, so there are different then use cases for data that you have to cope with. People want to export the data, so there's a sustained high I/O transfer from the disk servers, which have to be visible on the WAN. You also have this if somebody wants to transfer a whole data set to a CPU node for analysis there. The only difference, it has to be available on the LAN, but these are I/O intensive transfers. As well as these, you have people who have their batch jobs which will read an event, process it, read an event, process it, and so on. So there you have very low I/O impact on the disk servers. So as I say, they have a different footprint, these different transfer methods. And you certainly don't want to have a system which doesn't know what the user is going to do and will route 20 people who want to transfer the data at high speed to a single disk server. On the other hand, if you've got 20 people that are doing this low I/O analysis, you don't want to keep them waiting. You can route all of those to the same disk server. You don't want to say there's only 10 I/O slots and leave them waiting. So we looked at various different mass storage systems to see how they would cope with our sort of data load, the random access that we have. And generally, you know, the conclusion was that they didn't quite meet our needs. HPSS, for example, was very well adapted to streaming I/O, but not our random access I/O. So we put in a disk pool in front of that to handle the random access, and then we had to manage that. So in the end, we left ourselves with a system that was more and more capable and produced our own mass storage system, which we call Castor. So key features of Castor that relate to the challenge that I mentioned, well, this one doesn't, but it's database-centric. So this is certainly very good for coping with unreliable hardware. You can easily start, or unreliable software, in fact, as well. I should mention that if it's homegrown. You can easily restart any of these agents, and you don't create a problem for the overall system. Also important is the fact that there is no direct connection from an end user to any critical service. They all go through some gateway. So there's no way in which an individual user can create a denial of service attack, if you like, for others. Then we have, addressing the access problem I had before, scheduled access to I/O. The Castor system itself doesn't decide where any I/O request be routed to which disk server. Instead, we hand that job off to an external scheduler, which is in fact Platform's LSF, the same system that we use for our batch service. And we tell it the characteristics of the job in terms of its expected I/O footprint. LSF knows what the free slots are available on one of the disk servers, and will route the job to a disk server to make sure that nothing is overloaded, or it will just wait in the queue until a slot is available. Because we have this scheduling, we can also handle priority requests. So my request for a file shouldn't have the same priority as somebody who is doing recalling a bunch of files for the experiment as a whole, one of the production managers. So we can prioritize requests from privileged users with LSF, with our external scheduler, just in the same way as we prioritize the access to CPU for privileged users. So a picture of it nicely shows the database in the center, the different components around, and then shipping the data to the, between the tape subsystem and the disk subsystem. Performance, just some plots showing that we're getting there. These are from a while ago. We can sustain transfers then from disk 1.2 gigasecond. We can transfer data to tape at 1 gigasecond for a sustained period. You can't read the dates on that, but it was a test which took place at Christmas period when CERN is shut down for 2 weeks, so there was nobody around. So we're sustaining these transfer to tape at a gigasecond with hardware failing and no problem. There we can hit 2 gigaseconds to tape at peak. We can certainly do it for longer now than during that test. And these are some of the tests showing the I/O rates that we can sustain for individual experiments and aggregate over the last month. This is this year. So the performance we have at CERN is certainly acceptable with our Castor system. On the other hand, we have some interesting challenges ahead that we have to face. There's the issues of data lifetime, disk capacity, file sizes. We're not the only mass storage system in town, and we need to ship data out. So data lifetime. Our last accelerator started in 1989 and shut down 10 years later. So we used, over that period, at least 4 different technologies to store the data, starting with IBM 3480s. I think we didn't have any real tape at that stage. And then all of the data that we'd ever taken right back to 1989 was reprocessed and reanalyzed in 2001, 2002 with the final version of the experiment software. So if you translate this into LHC time, we're going to be running until at least 2020 for this. So what technologies will we be using in 2022 for the analysis then? Well, we don't know, but what we do know is that we're going to be repacking the data every 2 to 3 years. I've already talked about this in some senses about the media cost. So this is a time-consuming. It will be a major I/O process to add on top of recording the data. And we have to maintain the integrity of the data. Now, clearly, we're doing that with checksums if we're copying data for tape, but this data integrity issue is also starting to hit us now because we've got volumes of data on disk, we've got volumes of data transferred, where bit error rates in times 10 to the minus 13 actually start turning into times 1 or 2 events that we see. So looking at data integrity, both for these transfers and also in steady state operations is going to be a challenge for the future. Okay, disk capacity and I/O rates. I guess you can tell my original for this slide was from last year, but I think we're not yet using terabyte disks in production. But this shows what an individual disk has been able to do over the past 10 years. Capacity has increased, and I/O capacity, I/O ability has increased. So if you look at a terabyte, this is wonderful. 250 disks 10 years ago, 1 or 2 disks now. You're sitting pretty there. Certainly a lot less power consumption. But if you look at the I/O capacity that you have to that terabyte, we were getting 2.5 gigaseconds to the terabyte 10 years ago, only 120 megasecond to the terabyte today, which is not so good. So we now we're forced to buy different storage configurations, either capacity-oriented or throughput-oriented. Yeah, I've said capacity and storage on the slides, it's the same thing, but capacity-oriented or throughput-oriented for these. And this fragmentation of the disks increases the complexity of the things that we have to deal with, as well as making it harder for the people who have to buy them. Okay, file size matters. These curves, which are hand-drawn to make them visible to you, they're not that wobbly really, show the efficiency of the use of a tape drive depending on the size of the file that you're writing along the bottom axis, and the curves show how many files you're writing per mount. Now, today's drives are very performant, 100 meg, 120 meg a second, but that's streaming data to them. Every time you want to write a file mark, there's an overhead of around 5 seconds, which is equivalent to writing something like 400 megabytes. So if you're writing less than 400 megabytes, you're going to spend more time processing the file than actually writing the data. And unfortunately, at the moment, we're sitting somewhere down in this space, running at low efficiency for many of our files. We can't afford that. We have to move the experiments to moving much larger files and operate our tape park at much higher reliability. And this is definitely becoming a problem now. There are some of the tier 1 sites. I know one that is really not able to cope with the data rate that is being sent to it, not because of the data rate, but because it just doesn't have enough tape drives given the file sizes that are being used. So this is a challenge that we're going to have to address in the next year. Okay, so as I say, we're not the only mass storage system in town. Fermilab have a system called Dcache, which is a disk cache which will talk to multiple tape backends, NStore at Fermilab, TSM or others, and there's a disk pool manager for sites that have disk-only storage. So users don't want to know what the mass storage system is and use different commands. And more importantly, the experiment frameworks, you don't know where your job is going to be sent. It's the grid, remember? So you want a single interface to all of these systems rather than lots of if, then, else's to find out where you run, to find out what the mass storage system is. So there's SRM, the Storage Resource Manager from LBL, that provides a common interface to mass storage systems. And these multiple and independent implementations of SRM all talk to each other. So getting to this stage has been very difficult, but providing this common interface has been a really important tool to enable us to have successful organized data export. You need to have the data export, you need to talk to a mass storage system on each side, and as I say, you don't really want to know which one of these are. I think I've motivated the reason for the need to ship data, the raw data export, the analysis data updates, and so on. But this is complicated when you're shipping petabytes around. 0.1% failure rate, 99.9% success sounds good, but when you're shipping petabytes, a 0.1% failure rate, you can't rescue this manually or follow that up manually. You also have, coming back to the point I was talking about before about sites having their views of how things should be done, they will have policies. So they will want to allocate 50% of their resources to Atlas, say, 25% to CMS, and so on. And you don't want to see their network links saturated by data shipments for Atlas. So we provide for this a file transfer service developed as part of the EG grid development. Now, this is a service which allows a virtual organization to say, I want these data sets sent out to different places around the world, and FTS will manage that according to the VO policy and the site policy. It will provide prioritization between the VOs, as I said, to make sure that the site's resources are being done, but also within a VO, again, if I'm sending data out, then it doesn't matter. Whereas if a production manager is sending the data out, that needs some level of priority. Prevent network overload, well, we don't monitor the network management, we don't manage the network lines, but we certainly know what the capacity of a link is to sites and manage that. So this is an example that shows a plot that shows how much data we've been transferring out this year. And, well, I did say, remember 1430 megabytes a second, and this is the link here, the peak. So we've actually managed to reach, in our test this year, 1430 megabytes a second out from CERN, which is the rate in which we need to achieve in steady state operations in 2009. We won't need that in 2008. So we're getting to a level where we can ship data out now at the rate we need. Providing a network for that has also been a challenge. We have a set of dedicated links now to all of the tier ones, a private optical network. So setting that up has been a major challenge over the past few years. The bandwidth, not so much. In the 90s, we were really wondering how we would cope if we had 622 meg links between the different sites. Now we have 10 gig links. So this isn't a problem in terms of the network bandwidth, but organizing all of that has been. This just shows the plot for the network connections in Europe. I don't have one that goes wider, but when you think that countries like India are involved, getting a significant network link to some of the tier 2 centers such that they can collaborate effectively in the analysis of the data, I'm sure you can imagine that that's taken a lot of people who spent more time flying around on planes than I have to get that infrastructure in place. So we don't see it a lot, but it's certainly one of the challenges that the LCG project has had to deal with. Okay, so successes. We have a mass storage system at CERN that can meet the demanding requirements, so that's good, we've built that. And we have large-scale data transfers, which are essentially now routine between CERN and between the tier ones themselves, at the rates which are starting to approach those that we will need in real operations. On the other hand, we haven't really demonstrated yet that we can have all 4 of the experiments shipping their data out simultaneously, and we haven't yet really had to cope with the operations for large-scale user analysis. Most of the work so far has been for a controlled production set of users. So dealing with the analysis is something that we're going to have to ramp up to checking we can do with that in the coming year. Okay, so the last one of my challenges is what's going on. Well, this is something that I think people are starting to become ever more concerned about, because we understand the systems that we've got. Our service managers understand whether a box is up or down or whether its load is too high. But what about the overall service when the service comprises as many boxes? And what about the users? Do they understand the service? Cross-site issues are also very important. If I'm shipping data from CERN to Fermilab, then there are 2 different sites involved, lots of 2 different mass storage systems. There's multiple network providers. So who can tell you what's going on in these situations? So one of the things that we've added is to the top of our monitoring package at CERN is something which allows users to see more easily what the status of a service is. In the past, they've had access to our monitoring system, which is red all the time because you've got 2,500 boxes and they're never all going to be up. So it gives a very alarmist view of the situation. This gives a much calmer view of how the service is provided. So if you look at the top bullet, which is service for physics here, it's not 100% green because it's never going to be 100% green. We can never have absolutely everything of our service working perfectly. But on the other hand, the boxes that we have got up are able to provide the service level quality that we expect. So therefore it's colored green. On the other hand, down here, we're not able to provide the quality that we expect. So I'll skip the architecture. It provides a hierarchy of services, which is good because it can address services for different virtual organizations. Again, just like I had the dynamic clusters for the monitoring, you can have a service which is down for one virtual organization, whereas everything is working fine for another. And you have the ability to show this with SLS, as is shown here. The service for the different virtual organizations, they can be at different qualities, depending on how the different components. It might be a disk server has got critical data on for one experiment, and that you can reflect in this level of display. For a system manager, you have to understand then that the criticality of the different boxes and address those, and this allows you to see that. Okay, some other displays. If you look then more widely for the grid, there are various different sort of domains that you want to provide the monitoring. There's the grid applications, the user applications that are running. There are different grid middleware services that are running either centrally across the resource brokers that ship data to all sites, or at an individual site. And then there are local resources that are available. And there are many different systems across the grid for doing that. I've mentioned Lemon and SLS at CERN providing local monitoring, but many people use Nagios and Ganglia. How do you build these up into a coherent whole so you can understand that? Here is a deliberately busy chart that shows some of the many different things that are involved at different sites. And it's aimed to look complicated to show that really it's very difficult in this sort of world to understand what's actually happening. The data's complex, there are many sites. You've got nice sort of tables and bar charts which you can understand at a site. I showed some of those earlier. But where's the easily understandable top-level view that shows you quickly where you should go now to fix the most important problem and to help understand why jobs are failing? So there's a nice new visualization that's been introduced based on tree maps, where you have a display of different regions where the size of each region is given by some metric, its importance, either in terms of the size of the site or the number of running jobs. So you look at the big blobs of importance, not the little sites. And then you color the rectangles according to some other metric, like the overall status, the availability, or whatever. And so you can see quickly where you should be looking. Maybe it's more important to look at the big orange degraded blob in France, I think that is. Yeah, it's in France, rather than some of the red blobs in Italy. Fix the degraded blob and turn it back to green. It might be a better thing to do than fixing some of the red blobs because they're not providing as much resource. Okay, so these can be organized various levels. Top level, you can drill down to different geographical areas. You can look at sequences them for trends, and you can look to see at correlations. I think that this one is meant to show that if you look at there's a good correlation between some of the storage element status at a site and whether or not the site is actually up or down. The site information service is green for all of the sites, so you can look at what the different things are important by comparing these. Interestingly, this is starting now to be used at the SLAC. Don't ask me what this actually shows. To look at their batch systems, again, their major configurations. And you can see what's important by its size and spot trends and changes. So they're using MagnaView, which is, I think, a commercial package, and there's a link to a web presentation there. So these ideas about how you make things visually more important and bring out the visually better able to bring out the important information in the mass of data are key. So I'll leave, or not quite leave, but the problem I have at the moment is how you solve this. This is the ratio of the CPU to wall clock time that we have compared to the 85% efficiency we expect. You'd say that was the trend. Well, you could argue that I was being pessimistic in drawing that line, and actually this sort of average efficiency would be better. But now I'll show you what happened in September. The performance nosedived. Now, I actually have a good understanding of why this is. It's how you access it relates to data access. But what you want to be doing is spotting the trends early. You don't want to be faced with this level of performance when LHC is actually starting and see that everything nosedives the minute you turn the accelerator on or after 5 weeks. Okay, so summary. I think we've got an immensely complex situation, worldwide distribution, amount of data, whatever, that's given us a lot of challenges, that many of which you've addressed, I hope, successfully in the last 5 to 6 years. We have a worldwide grid service, which, however much there are problems with that, is an achievement, considerable achievement. We're shipping petabytes of data a month around the world between sites. So there's been a lot of progress over the past 5 or 6 years. On the other hand, we're nearly at the stage where we'll be getting real data. We need to understand if we can cope with the chaotic users as well as the scheduled work. And coming back to the things that I've just said, will we be able to identify problems early and fix the underlying causes when we have the real data? We plan major dress rehearsals in February and May next year to test this, which is our last chance to do that before we get the real data in from June. So next November, maybe we'll have some answers to whether or not we really have addressed successfully the challenges of LHC computing. Thank you.
Hi, Doug Hughes from D.E. Shaw Research. Over here. I thought I had a really cool job. This is amazing stuff. There's been a lot of talk this conference about sort of undetectable errors, and especially when you get to large sizes of data, how that can influence your data, that you read something that you don't necessarily have a checksum beforehand of what it was supposed to be. And you think it's correct, but it isn't. I'm wondering if you've seen this or if you're even looking for this, and if you have, what are you doing to deal with that sort of issue?
Okay, so the question relates to undetectable data errors where you're reading back something which isn't what you thought you were reading back. Yes, it is definitely a real problem for us. We have seen that. We've seen silent data corruptions. There's an interplay between a huge range of things. There's the file system, there's the RAID array, there's the disk, you've got memory involved. Really, what we can, at an application level, there are things in a number of the data is actually essentially zipped. So an error in the data will actually cause a problem at the application level, we hope, in many cases. But that's not our responsibility to track that. At our level, what we're looking at is scanning the data, which is on disk, rereading it, putting end-to-end checksums in where we can. It's I'm sure it's not an easy solution to get a real end-to-end checksum for everything that you're doing, but we're trying to do that. And scan the data that we have on disk. This again comes back to some of the I/O rates that you have to deal with on the disk servers. You have to add in the I/O rate that you want to do to scan through the data to achieve that. And to be honest, Fermilab have been doing some of this scanning a lot better than we have for a while with the Tevatron. But I think I said that the 10 to the minus 13, 10 to the minus 15 bit error rates, the volumes that we have for the transfers, they translate into real errors.
Thank you.
Would you mind, while you answer a few questions, would you mind throwing the slide back up that has the network map on it? I'll just look at it while you answer other questions.
I'm not sure whether I should mind. I shouldn't mind, but it might mean that it's not actually correct. Well, I mean, it is correct, but I don't know anything about it because I'm not a network guru.
It's probably close enough for my curiosity. Thank you.
Okay.
I'm Brad Knowles. I'm from the Network Time Protocol Project. I was just wondering how you find your NTP servers are scaling. Are you using them in unicast mode, broadcast mode, minicast?
Sorry, I didn't quite catch that. How do we?
I'm wondering about your NTP servers and how well they scale. You've got several thousand clients, and we've discovered that at least in some usage modes, that causes the NTP servers to be kind of overloaded. And I'm just wondering if you're using yours in broadcast mode or.
There's still some service that I didn't quite catch. The NTP service?
Network Time Protocol.
Oh, okay, the NTP. Sorry, I'm not.
Sorry, I didn't have the microphone adjusted.
Okay. I wouldn't like to comment on that. I mean, I'm not sufficiently knowledgeable about that area. Sorry. If you come back to me later, then I can give you the email address of people who could answer that, but I would just make a fool of myself.
Okay, thanks.
Hi. Assuming your budgets are reasonably fixed and predictable, do you ever sit down and say, the most cost-effective thing we can do is wait 6 months?
No. I am actually one of the, well, it's not strictly true. I mean, there are people that certainly do say that we should wait, but the problem with waiting 6 months is, you wait 6 months more, and the capacity isn't there sort of now to do the analysis. The more serious part answer to your question, though, comes back to the issues that we have in procurement. There are people who say, it takes me 3 months to get these boxes. I'll start the ordering process 3 months before. I think they're not used to the scale of buying 2,500 boxes. It doesn't take 3 months to get them from delivery, from the moment you start to actually commissioning. There's a whole set of processes you have to worry about. And there are also hardware failures that you can have with the boxes when they arrive. And you have to be able to cope and recover from the fact that some of the kit that you've just delivered has a fatal flaw. We've seen, I'm sure everybody's seen, disk firmware problems, disk problems, that you have to leave time in your procurement process such that those could be resolved before you actually need the disk. If you buy them at the last possible minute and you have a problem, then you have no kit at all, which is worse than having less than you could have had if you'd bought it 3 weeks later.
Hi there, John Wilson from GFDL. I've got a question regarding the distributed nature of your compute and your data. So this implies that the user jobs need to know the size of the data sets they're working with?
Sorry, the distributed nature, do you understand the size of the data set?
Yes, because you're dealing with distributed computing, and your data sets are theoretically sourced at CERN, but are distributed out. So your user compute jobs need to know the size of the data that they're going to be working with, and when they're going to be needing it, potentially? Okay,
so do the users need to understand the size of the data that needs to work with? Actually, not so much. The analysis is, what the users will tend to want to do is run over a couple of hundred, a couple of thousand events to check that they're getting something which looks reasonable. And then when they're sure that their analysis is working, they want to run it on all events of a given type. So the more relevant point is the metadata associated with events that says that these are a subset of events that we think are candidate Higgs events. And then somebody will say, I want to process, send my algorithm to process all of these candidate Higgs events. And the issue there is actually finding all of these and checking where they are. And so it's not so much the size, it's the ability to check that you can actually find all of those. And there is a huge metadata issue that I haven't covered, but we do have a file catalog which tags data according to the type that they are and which data is at which site. And a bigger challenge, a challenge as well, is making sure that that is coherent with what the mass storage system actually has at a site if a disk server is down. So yes, there are challenges there, but not so much related to the size of the data set.
Okay, excellent, thank you. One other question. When you're transferring your data around, are you encrypting the data streams?
Are we encrypting the data streams? No, I don't believe so, no. I mean, there is some level of encryption of the protocol up front, and there is security testing and identity testing to check that, such that, say I am shipping pornography to your site, that you can find out that it was me that shipped it, but the data is not commercially sensitive. Now, there might be some encryption that Atlas are making sure that CMS can't read their data, but I don't know about that.
Okay, thank you very much.
His second question was actually my question. Thank you.
Okay, no problem.
Hi, Bill Cheswick, AT&T Research. A few years ago, there were some attacks on NSF sites by hackers.
Yeah.
And it occurred to me that there might be a group of people out there who may actually have a political desire to corrupt scientific data, to put in the dirty word nebula in the Sloan Digital Sky Survey. Have you seen, or do you consider this as a threat model, that someone might actually try to corrupt bits of your data and ruin the science?
Do we consider that as that people might want to actively target our data as a threat model? Actually, I don't think we'd ever consider ourselves sufficiently important. That's not one that had occurred to me. bigger worry that we have is that people see these as resources that they can use as, to mount a denial of a service attack on somebody else. Corrupting our data, I'd have to go away and think about that one. I guess we probably don't think anybody would do that. Would it matter? How would corrupting our results change anything? No, I don't think we have thought of that. Interesting, worrying thought.
Sorry, I've ruined some night sleeps before.
Certainly, certainly.